superposition concept from physics nicely captures this human intuition that we have. The superposition principle also is related to another important principle from quantum physics. How is it that humans are like electrons? What is it that we have in common? I don't know if it was Wheeler or Wigner once said, what we observe in this world is what we choose to observe, and that determines what we do observe. So our choice of what to observe actually determines what we observe. Humans don't reason classically. They often violate classical axioms. And so one reason it's important to use quantum reasoning if you're trying to predict somebody else's behavior. If you're trying to predict their behavior, you might make the wrong prediction if you're thinking that they're reasoning classically.
Jerome Busemeyer, distinguished professor of Indiana University of Physiological and Brain Science. He is one of the founders of mathematical models of human judgment and decision-making behavior. He wrote the book called Quantum Models of Cognition and Decision. Do you remember when you sense ambiguity about all possible decisions simultaneously? Or you try to figure out possible outcomes of something that is just a mechanical cause effect? Today we will ask all these questions and even more to Professor Jerome Busenayer. Hello, Professor.
Hello, everybody.
I'm really happy to have you on my podcast. It's something about science and business and life, because I was reading your book and your paper, and I was amazed about your approach and in general quantum physics approach to cognition. So I think we can talk about three main components of quantum approach to our brain. It's a quantum brain, it's quantum consciousness, and quantum cognition, which is your main subject of interest. So, but in the beginning, I would like to give our audience some general view on what is it quantum to our brain, and why in general we should apply quantum physics to understanding our consciousness and our decision making.
Yeah, so you want me to answer that?
Yes.
Okay.
Please.
All right. Well, I think there's several properties or principles from quantum physics that I think are generally applicable outside of physics to psychology or even economics. And so let me go through several of these principles, and then I'll talk about some applications of these principles in psychology and then maybe in business. So first of all, one of the main concepts that really captured my attention from quantum theory was the concept of superposition, of course. And, so that concept really related to me because, when we make difficult decisions, we really feel ourselves in conflict, and we really feel like we're in some potential to do either action at the same moment in time. It's not like we're in one state at one moment and another state the next moment and jumping around. It's like we're really fuzzy or distributed in our values about what action to take. And so that superposition concept from physics nicely captures this human intuition that we have. Now, the superposition principle also is related to another important principle from quantum physics. And, how is it that humans are like electrons? What is it that we have in common? Well, one of them is that both humans and electrons are sensitive to measurement. When you measure the position of an electron, you change its state. And so the measurement changes the state of the system. So it changes like a superposition, like an electron could be like in a spin up and spin down direction. It could be some superposition of those two states. And when you measure it, it collapses from the superposition to a single state, which then changes its behavior in the future. Well, humans are like that. We're sensitive to measurement too. When you ask me a question, before I have an answer to it, I might be superposed about that question. But then after I formulate an answer, I collapse and become clear about that question. And so that changes me. So I'm sensitive to the measurement. For example, like, let's say I go to a movie and some kind of movie, and I walk out of the movie and my wife asks me, well, did you think that movie was romantic? And, I was thinking about getting a beer at the time. I didn't really have any idea about romance, but then I had to think about it. Well, was it romantic or not? And I come to some conclusion. Yeah, I think that movie was romantic. And so if somebody asked me later on, was it a romantic movie? I say, yeah, that was a romantic movie. So it changes my state. So, and so both these two things, superposition and sensitivity, lead to a third important principle of quantum theory. And as everybody knows, quantum theory is a probabilistic theory. It's an indeterministic theory. I mean, our behavior is not predictable, perfectly predictable. So just like electrons, when you measure its spin, there's a chance it'll be spin up and there's a chance it'll go spin down. And you can't perfectly predict that property of the spin ahead of time. And humans are like that. So we are not perfectly predictable. Now, one of the important ideas of quantum theory that comes from these three principles so far is that before you measure the system, it doesn't have a particular state. Like an electron is not, right before you measure it, it's not in a spin-up state or a spin-down state. It's not either one of those states, but after you measure it becomes one of those states. And humans are like that. Before you asked me this question about the romance of this movie, I'm not in either state. But after you ask me that question, I become that state. So measurement is not just recording something that existed previously. Instead, it's creating something that didn't exist before. So measurement has this creative aspect to it. And I think, I don't know if it was Wheeler or Wigner once said, is what we observe in this world is what we choose to observe. And that determines what we do observe. So our choice of what to observe actually determines what we observe. Now, another very important concept from quantum physics that I think is applicable to more generally to human behavior, maybe even outside the economics, is the principle of complementarity. So complementarity refers to the idea that, we have two ways of looking at the world, and they're both required to understand the world, but they're mutually exclusive. So we can only look at the world from one of those perspectives at a time, in the sense that we have to kind of look at one perspective of the world and evaluate it from that one perspective, and then kind of rotate and change our viewpoint to another perspective. And you can't be, since it's kind of a perspective problem, you can't be in both worlds at the same time. So that's the complementarity problem.
Yeah.
So for example, like
I'm in business.
Yeah.
Actually, yeah. So because usually we have to choose between two sides of the coin, and we cannot see both sides at the same time.
Yeah. Well, it's like if I'm trying to decide what movie to go to with my wife, I can think of the movie that she wants to go to first. That's like looking from her perspective and try to evaluate that. Then I can turn around and say, well, what movie do I want to watch? And I can't do both at the same. I can't be both people at the same time. I have to put my feet into her shoes, and then I can put my feet into my own shoes, but I can't be in both shoes at the same time. So that's the principle of complementarity. But also related to that principle of complementarity is the principle of non-commutativity. So not only are things complementary, that we can only look at one thing at a time, the order that we look at these things makes a big difference. So for like a spin, if I spin up and spin down and then measure spin left and right, I'm not going to get the same answer if I did those tests of the spins in different orders. Well, humans are like that too. So if I go to this movie and my wife asks me this question, do you think the movie was romantic. And then I make a decision about, romance. And then she asks me, well, did you think it was immoral? And then I have to make a decision about morality. But if I ask those questions in opposite orders, I might come out with different answers. Or like, for example, a judge, judging a criminal offense, if the judge has to decide the punishment before judging guilt or innocent, they might come out with a different punishment than if they judge guilt or innocent and then the punishment. So the order that we ask these questions make a big difference. So that's a really key property that humans have that we share with things like electrons in quantum physics. We have this non-commutative reasoning process. And so we need a theory of reasoning that incorporates this feature that we have this non-commutative property. I'll come back to that in a minute when I talk more about probability theory. But so now another thing that these principles imply, they're not all really logically separate. They're kind of like connected together. Another principle that we buy into once we adopt the principle of complementarity and non-commutativity and sensitive measurement is the uncertainty principle. So how does this happen with human behavior? I mean, we know with particles, if you measure the position precisely, the momentum is kind of spread out and uncertain. Or if you measure momentum precisely, the position gets spread out and uncertain. Well, humans are like that too. So if you become clear on one question, that might make you unclear on a different question. And so one question might disturb another question, causing some uncertainty. So for example, like on this question of romantic aspect of this movie versus the immoral aspect, once if I resolve my opinion first about it's romantic and make that clear in my mind, but then I'm asked a question about, well, is it immoral? And now when I start thinking about the morality, I make that question clear in my mind. But once I make the question on morality clear, I might become uncertain about my answer about romantic. So I might initially think, oh, it's romantic, but then I think it's immoral. And then I might think, well, maybe it's not romantic. So answering the moral question might disturb and make me uncertain about my romantic answer. So that's a sixth principle, basically. And so the last principle that is important in quantum theory, of course, and a big deal in quantum computing is the principle of entanglement. That's where all the speed of quantum computers come from. But how's that related to humans? Well, yeah, it's kind of a subtle question. Now, like, if we really wanted to see entanglement in a quantum sense, what we do in quantum physics, we have two particles collide and they go far, far apart, and we measure one particle and instantaneously has an effect on another particle in a distant part of the universe. And so that's kind of the entanglement effect. Well, how will we do such an experiment with humans? I mean, we could put two humans in two different rooms in a kind of a game, and one human could be trying to predict what the other human's going to do, but that's kind of like telepathy, and I don't know if that really happens. Some people think so, but I don't know. But that's one sense of, entanglement. But there's a more subtle, maybe even deeper sense of entanglement that's important in cognitive quantum cognition, and that is that our judgments are very contextual, and so the context of questions then can change the answers. Like, when you ask a pair of questions, A and B, do you think the current president is doing a good job, and do you think the country is going in the right direction? You ask these kinds of questions. Your answer to is the country going in the right direction might change depending upon if you asked it in the context of also asking the president is doing a good job. And so the answers become dependent upon the context. And in order to explain these kind of context dependencies and judgments, we need the concept of entanglement. So those are several principles, I think, that come from quantum physics, but are applicable outside of physics to, cognitive psychology or even economics. And that's a principle of superposition, sensitivity to measurement, indeterministic nature of behavior, complementarity, non-commutativity, uncertainty principles, and entanglement. Now, let me say something more general about quantum theory and quantum cognition. Now, people have different views about quantum physics, and I don't like to say we're doing quantum mechanics. Quantum mechanics is quantum physics. But what happened in the 1920s, when the quantum physicists, Bohr and Heisenberg and Schrodinger and Dirac and everyone, when they invented quantum mechanics, and Bohr especially, they invented a whole new probability theory. So, and so we have more than one probability theory out there. Most of us are trained in what we call a Kolmogorov probability theory. Kolmogorov was a Russian mathematician, probabilist. And Kolmogorov actually axiomatized classical probability theory in 1932. Of course, classical theory was developed in 1700 and 1800s by Laplace and other people, but it wasn't axiomatized until Kolmogorov axiomatized it in 1932. Now, about the same time, von Neumann took the ideas from quantum mechanics and axiomatized it, and so axiomatized quantum mechanics in terms of quantum probability. And so we have this general theory, two general theories now of probability. There's the Kolmogorov theory that most people are trained in because it's kind of the classical theory. And then we have the quantum probability theory, the von Neumann theory. They're based on different axioms. And so what are the different axioms? Well, I'm not going to go through the details, but the basic idea of Kolmogorov's theory is that we have these events in the world. If you purchase this new option for an investment, you're going to succeed. That's an event. Kolmogorov theory is based upon the idea that events like, your investment becomes successful. That event is represented as a subset of a sample space. And so all of Kolmogorov's theory is based upon the logic of subsets. And the logic of subsets is a Boolean logic. And so when you buy into a Boolean logic, you're buying into a number of axioms, and these axioms include closure. So if A is an event and B is an event, then the conjunction is an event. If you invest in here and win and you invest in there and win, well, the conjunction, you invest in here and there, that's an other event. And that's like the intersection event of the set. And then you also buy into not only closure, but commutativity. So A and B is the same as B and A because that's the nature of intersection. And then you also buy into distributivity, like the event A and B or not B, A parentheses B or not B, is A and B or A and not B. So you're buying into all these axioms at once when you buy into Kolmogorov theory. And I'll maybe make this intuitive with some experimental results in a few minutes. But quantum theory, how is it different? Quantum probability is based upon a different idea for events. So events in quantum theory are subspaces. So subspaces like a plane or a line or a hyperplane. So you have a vector space. An event like being successful in a investment is like a plane in that subspace, in that vector space. And so you're buying into the logic of subspaces instead of the logic of subsets. And so the logic of subspaces, sometimes we call this quantum logic. Anyway, has different axioms. And so in a way, quantum probability is a generalization of classical probability. We relax some of the axioms of classical probability theory. So for example, the axiom closure doesn't necessarily hold. So for example, an example when I was talking about movie and immorality, these two events, the event A, that I think the movie is romantic, might be one event. The event B, that the movie was immoral, might be a second event. But there's no A and B. And the reason why there's no A and B is because they're order dependent. There's an A and then B, but I won't get the same answer as B and then A. So there's only a sequence of events and not a conjunction. So we lose closure because we have to deal with non-commutativity. So non-commutativity is the second thing. So A and B is not the same as B and A. Yeah. And third, we lose distributivity. So A and B, parentheses, B or not B, is not necessarily equal to A and B or A and not B. And so let's take an example of distributivity. Like this judge, if this judge is trying to think about a criminal, like let's suppose we take the event where the judge is just trying to decide the punishment. Well, what should the punishment be for this crime? Should it be put to death or not? We have death penalty in this country. Yeah. So it's controversial, but – so that when the judge makes that decision about should this person be put to death or not? That's an event, punishment event. Now, in quantum theory, when the judge is deciding punishment, he's not asked to resolve the question about guilt or not guilt anymore. So he can remain superposed about those two questions. And so what happens is he can decide the punishment without resolving or become clear about the guilt or not guilt. In classic theory, that cannot happen. In classic theory, if he's got to decide the punishment, he's got to first decide whether he thinks the person's guilty or decide whether he thinks the person is not guilty. It has to be guilty in punishment and guilty in not punishment. But quantum theory is not necessarily the case. You can be deciding punishment without resolving the guilty and not guilty question. Or like I can decide this movie is romantic without resolving ahead of time whether I think it's moral or not. You know, when I decide it's romantic, I'm not thinking about morality yet. And so I can resolve one question without resolving all the question.
If we think about application for decision-making, what exactly is the difference in a simple explanation between quantum decision-making and classical decision-making? As I understand, quantum decision-making enables us much richer decisions and to have infinite thinking capabilities about decisions. But what exact difference? Why quantum decision-making and people who are successful, I think they apply quantum decision-making unconsciously because they are built this way. And some people should learn how to do it in order to uncover some superpower in order to decide in business and in life. So what's the difference? Why it's better to learn about quantum decision-making and apply it?
Yeah, well, that's a good question. I mean, we might ask the question, well, why in this world should people use quantum reasoning when the world we see is classical? I mean, electrons are, micro things. We can't see electrons, but we see baseballs and we see water waves. And these are all classical.
We're built on electrons and atoms. We don't see atoms, but we see what result of all these.
Well, that's the point. The point is people often say to me, well, the world we see is classical. Well, the billiard balls and the water waves are classical, but my dog is not necessarily classical when he's chasing the cat.
Right.
And in fact, humans are not classical because we do experiments and we see evidence showing that humans don't reason classically. They often violate classical axioms. And so one reason it's important to think about, use quantum reasoning if you're trying to predict somebody else's behavior. If you're trying to predict their behavior, you might make the wrong prediction if you're thinking that they're reasoning classically. They may not be reasoning classically. I mean, sometimes people do, sometimes people don't. When I mentioned before, quantum theory is a generalization of classical probability theory. It's a generalization in the sense that in classical probability theory, you have this commutative property. Well, in quantum theory, sometimes events are commutative, so it doesn't matter which order you ask, and sometimes they're non-commutative. So quantum probability is a more general probability theory that allows for non-commutativity. So, for example, if you ask me what's my age and what's my occupation, it doesn't matter what order you ask me that. I'm going to be commutative.
Yeah.
But if you ask me about the romance of the movie and the morality, I might be non-commutative. And so quantum theory allows for this non-commutativity in reasoning, and we have to take that into consideration when we start predicting people's behavior. So let me just turn to an experiment, for example. Let's say, here, this is a real experiment, but I'm going to try to put it more in a business perspective. But this is an experiment done by Amos Tversky and Eldar Shafir in the 1990s. They gave people gambles, and they use what they called a two-stage gamble. So this is like making a business investment, right?
Yeah.
I mean, the gambles, you win $100 or you lose $50. So I think it's a 50-50 gamble, so the expectation is positive. I mean, if you just go on the expected value, you should choose the gamble. But people are risk averse, so they don't always do that. So that's not the quantum part. That's just regular economics. But the interesting thing about their experiment is they were using a two-stage gamble because they wanted to test the principle of rational decision-making called the sure thing principle. Now, in this principle, basic idea is if under one state of the world, you prefer to take the gamble, take this investment, and under some other opposite state of the world, you still prefer to take this investment, then you should go ahead and take the investment without knowing the state of the world. That's called the sure thing principle. That's the foundation for Savage's theory of subjective expected utility theory, which is a kind of a rational theory of decision-making used by economists. Well, Tversky and Shafir wanted to test that principle, so they gave people this two-stage gamble. And so on the first stage, it was mandatory. They had to play the first stage. So they played the first stage, and then they were asked whether or not they wanted to play again after the first stage.
Yeah.
So, and they had two conditions. Well, let's say three conditions. And one condition of the experiment, they were told they won the first gamble. Well, you just won. You won $100. Now, do you want to play again? You win $100 or lose 50. Now, and when they were told they were won, most people wanted to play again. They figured, well, I got extra house money, I can play again. So then another condition, they were told, you just lost the first gamble, so you lost $50. So then they asked, well, do you want to play again after you lose? Again, most people wanted to play again because they wanted to make up for the losses. But when a third condition, they weren't told the outcome of the first gamble. So they knew they played the first gamble, but they didn't know what the outcome was. And so then they were asked, do you want to play the gamble or not? Now, when they weren't told the outcome, they changed. And now most people wanted to play the gamble again. So most people didn't want to play the gamble. So when they didn't know the outcome of the first play, most people didn't want to play the gamble again. So when they knew they won, most people wanted to play. When they knew they lost, most people wanted to play. But when they didn't know, they changed their mind and they didn't want to play. So that violated the sure thing principle. And so that's now how does quantum theory deal with that? It's because when you're just, we have a mathematical model for all this, but briefly, intuitively, when you're asked do you want to play the gamble after knowing your win? So like your first gamble, you're initially on the first stage gamble, you play this gamble, you don't know if you're won or lost, and so you're in a superposition state when you're starting out. But then you're told you won, so now you've collapsed. So you're in the win state, and given that win state, you're asked to make a decision. Yeah. Now, or you're in the superposition state and you're told you lost, so you collapse to the lost state. So you're in the win state or lost state, and then you make a decision. So the decision is based upon these collapse states. But when you're not asked to, when you're not told about the outcome of the first play, you're remaining in the superposition state. Now, what happens when you're in a superposition state is you can get these interference terms, because when you calculate probabilities of quantum theory, you have an amplitude A plus an amplitude B, take the squared magnitude. And what happens is you get the square of the first amplitude, we achieve the probability that you get if you were told the first outcome, and then you get the square of the second amplitude, which is the probability that you would get if you're told the second outcome. But then you get this cross product term, which can be negative. And so because you're in a superposition that generates these cross product terms, interference terms occur from the superposition effect, and then you get this drop in the probability when you don't know. So when you're told the outcome, you're eliminating this interference term. But when you're not told, the superposition generates this interference that drops the probability. So this is something to be important to know about when you're making decisions, that this kind of interference can happen when you're making decisions.
I remember one of your talk. You talk about buy, not buy decision. So you have some two axes, buy, not buy, and some superposition between them. So I just imagine I'm getting into the shop. I didn't decide should I buy it or not, or what should I buy actually. And in this case, I'm exactly in this superposition state of my mind. But interesting, I cannot decide by myself. By the way, you mentioned about self-measurement problem.
Yeah.
I cannot measure myself. I cannot collapse to some decision by myself. So I need sales manager who approach me and start to influence on my cognitive mind, which is in superposition state. Or even I collapse, I get with decision, I want to do this. And this is interesting subject because I didn't find some mention of this. And these guys start to ask me to redecide. So I'm already collapsed, and he gonna get me again back to superposition state.
Yeah, that's like the uncertainty principle. Like you could be collapsed, just like the romance versus morality question. You could be collapsed on romance, but then when you're asked about morality, you become unclear about the romance. Yeah. So you could be collapsed up on, I want to buy product A, but then the salesman comes over and kind of rotates you away from that answer, and now you're become uncertain about what you want to get. Yeah, so that's an example.
Also, you mentioned a role, you didn't name it, but a role of intuition. And we know in business, intuition is at 50% of success. Mm. So this comes from quantum condition, right?
Mm. Yeah, I often think that we often think that the superposition state is this intuitive. It's kind of like almost an unconscious intuitive state, the superposition state. I mean, you might have some kind of vague feeling, but the collapse becomes when you become conscious. You know, we often associate the collapse with consciousness. So you're kind of in this working in this intuitive superposition state. And I haven't talked about the dynamics, probably don't have time for that, but in quantum theory, the dynamics, you kind of process many alternatives in the superposition state in parallel. That's where the power of quantum computing comes from, because it can search many different paths simultaneously, except you have to ask the right question, extract the information from the superposition state. But while you're in a superposition state, you're in this state where you can kind of parallel process many paths, explore many paths in parallel. But then when you collapse, you're forcing a decision, and then you're coming out of the superposition state and becoming more conscious of what action to take.
I'd like a little bit dive deeper into difference between cognitive state and a record state, because it's actually the core of theory. So you mentioned that what we observe is determined what we choose to observe.
Yeah.
So I remember there is also a Russian professor. He wrote a book about how to create a reality, and he guessed that we create reality. So by collapsing our measurement, we create reality. So we live in infinite realities, and we create what we want.
Mm.
So I would like to dive deeper into this stuff, because it's very interesting. Because if, for example, I think that in a year I will make X, Y, Z, and I created this reality in my mind already. So all my decision making is directed like a vector towards this outcome. But outcome, as I understand, this is mechanical definition. We're talking about, maybe I was thinking about how to define quantum thinking, and it's a vector. So instead of outcome, we're talking about vector. Maybe strategy belongs to quantum cognition. Strategy because it's vector, it's a set of decisions towards some outcome, and outcome is a pure mechanical stuff, but the process towards the outcome is a quantum.
Mm-hmm. Yeah, I mean, I think that's getting more into the nature of the dynamics of quantum theory. And in quantum theory, it's like when you're trying to make a decision, you're in this some kind of superposition state where you haven't made up your mind about which one. It's not like you're jumping from, oh, I'm going to make this investment to now I changed my mind and make this investment. You're processing both of these at the same time simultaneously. So you're keeping your options open basically, and processing both paths in parallel and it's a vector basically mathematically that's being rotated in space across, well, in some kind of vector space.
Yes.
Across time. And not until you make a final decision does this vector, well, it collapses to another vector, but it collapses to the outcome of the decision. But before that, you're in this superposition state, which is actually processing many alternatives simultaneously. It's kind of like a way of parallel processing and keeping your mind open rather than collapsing and closing off options too early, I would say. I think that's a power. The powers of quantum reasoning is to kind of parallel process ideas before you collapse onto a single idea and get stuck in a local minimum.
And create your reality finally.
Yeah, the questions you ask, the measurements you take in life create your reality. So, yeah, right. If you don't ask these questions, then you won't become these states. Then the questions actually, generate the outcomes that you observe. So that's an important aspect of quantum theory too.
Yeah. So actually, consciousness. What is it? Consciousness is all about creation of our reality. So consciousness, reality manifests from the consciousness.
Yeah, I mean, consciousness. I kind of think of consciousness is when you start to record in memory something in particular. So your memory is a record of what you're conscious of. The superposition state is really pre-conscious, I think. So you really got several things in process that are fuzzily and distributed across time, and then all of a sudden one will become crystal clear. Then you record that. You become conscious of it and record that. Maybe even verbalize it to people. So you commit to that decision.
Yeah, I developed so-called quantum business thinking methodology that helps people to be conscious about this consciousness process of creation reality. Yeah. Because people don't aware it. They don't think. They think they decided. Not. I always talk about two people in one body. And these people could be lying, and these people could be totally struggling each other. And this is a big problem for people. And how to align these two minds, conscious mind and subconscious mind, within one body towards specific goal. I want something, but subconscious mind doesn't allow me to do it. And this is a big problem. So if I understand, and thank you for helping me, and maybe you will help other people from our audience to understand these dynamics, it's much easier to decide and to see and to predict what happens from your decision, not just cause effect. Okay, I do this, I have outcome like this. I do that, I have out. Usually it doesn't work. For me, if I apply my logical decision making, I lose all the time. So when I listen to my intuition, this is where I win. So it's very important application. So we are going to wrap up. Okay. And my last question.
Yeah.
Could you define what is it quantum happiness?
What? Say that again?
What is it quantum happiness?
Quantum happiness?
Yes.
Well, what is quantum happiness? Well, I mean, maybe when you see different perspectives and freely move from one perspective to the other, so you have a better understanding of the world.
Yeah,
be able to see different people's perspectives and be able to change your perspective and see the world from different perspectives, and you might be able to understand the world better, and that'll give you some peace.
It means if we can align with our world, this is where we find happiness.
Yeah.
And this is actually belongs to quantum understanding and quantum dynamics of our mind.
Yeah, align our state vector with the direction that makes us most happy.
Yeah, thank you very much.
Okay.
I'm really happy to have you on my podcast, and I hope we will meet again, because we just talk about some surface of the problems you are solving, and I wish you to help us to understand how to align our lives with our work.
Yeah.
And influence on our work as well at the same time.
Yeah, right.
Yeah.
Okay.
Thank you very much.
Well, thank you for inviting me.